Okay, thank you very much. So, okay, I will comment a bit on what I wrote. So I gave a third example of so an Auslander-Reiten quiver above and the corresponding cluster variable. So now I took this quiver, so you realize that it looks very much like the oriented H3 quiver that I gave once, just to change a bit. I put this orange part, which corresponds to the orange part of Pierre-Guy in the last talk, but you can ignore it for a while. And here I recall where I stopped last time. So I take C as field now for simplicity. You could generalize certain things to more general field, but I really prefer to explain things over C. I take Q a Dynkin diagram, and maybe at the end, if I have time, I will explain you how goes a bit the more general case, a representation of Q, and to this I associate a certain Laurent polynomial. So, okay, in Pierre-Guy's talk and probably in Bernard's talk as well, it was written CC. For some reason, I write it X at this point, but let it like that. So it's GRE of M was the Grassmannian of submodule or subrepresentation of M. It's M of certain dimension vector. And Euler characteristic was the tool which permits us to measure the size of this Grassmannian. Then we had the Euler form, which has two different expressions that I explain you why they are the same in this case, and I might need to use both, but this is a bilinear form. So pay attention. In this case, it's obvious that it's a bilinear form. In this case, it's a proposition. It's not difficult. It's only for quiver. If you take a general algebra, you need to bring some modification to make that a bilinear form. What do I mean? Even the fact that it depends not on M and N, but only on the dimension vector is not a priori easy. Okay, it's true for a quiver. Then the theorem that I told you at the very end, or not at the very end, but almost at the very end, was these three kinds of identity. So if you take the direct sum of module and you compute the Caldero-Chapoton formula on this, you find the product. If you have an AR sequence, the product of the two n term is almost the middle term, up to 1. And if you have a projective, so I number my projective in such a way that Pi is the projective cover of the simple representation at I, meaning the representation which have only one non-zero vertex at 1. But just to number them, and then I have this formula. And I told you that in this specific case, it implies the famous theorem that you heard several times now, that essentially you describe all cluster variables by taking rigid module. In this case, all modules are rigid, plus the initial cluster variable. And then, yeah. So what was the reasoning? The reasoning was that this identity permits you to check the exchange formula coming from AR sequences, including the orange one, but the orange one are the third case, actually. The orange part is encoded in the third case. So it permits you that at least these two diagrams correspond, and then you need a counting argument to say that actually there are no others. Because of course, by doing this lazy mutation only at source and things of the quiver, you might miss something. So this is actually some theorem that you don't miss anything, and to do that, you need a counting argument. You need a counting argument. Okay, so my plan first is to prove this theorem, and maybe if I have time to explain you a few generalizations. And don't hesitate to ask me questions if there is anything unclear. So, what does it amount to prove this formula? This formula kind of the same shape each time. They compare some Caldero-Chapoton formula for different modules. So this thing is almost like a, I don't know if I should say a generating series for the Euler characteristic of Grassmannian of submodules. And if you are used to compute with that, you kind of know or guess that to prove, for example, this formula, the difficult part will not be in dealing with the exponent here. And in this case as well, you can imagine that it will not be the difficult part, but that actually the difficult part will be in comparing Euler characteristic of submodule of certain different modules. I mean, why the Euler characteristic of M of Grassmannian of submodule of M or submodule of N are related to this direct sum, or why this one is related to this two. This will be the difficult part. The exponent here will be just basically some linear algebra by summing up some bilinear form. It will not be the difficult part. So I will focus mainly at understanding this Euler characteristic. The other part of the computation will be somehow straightforward up to some technicalities. Okay. So for that, I will study a bit more general situation. I consider a short exact sequence of the following form: A, B, C. So very generic short exact sequence, and I fix some E, some dimension vector. I fix some dimension vector for the quiver Q. And then I define the following map. So I will define it naively, and I will try to give more detail. I will call it big phi E, and it will be the central tool for this thing, for this proof. It goes from the Grassmannian of submodule of E submodule of B, and it goes to something that I will write as a joint union for E prime plus E double prime equal E of Grassmannian of E prime submodule of A cross Grassmannian of E prime prime submodule of C. And there is a natural way to create at least point-wise such a thing. So let's call that, maybe, how did I call them, F and G? That's not so original, these two maps. So suppose that I take a sub-representation of B. How can I get a sub-representation of A? There is a kind of canonical way to do it. Just taking F minus 1 of, it should be B prime, F minus 1 of B prime. And then how to get, I will put a comma, a sub-representation of C. Just take the image of the representation. Okay. So you can do that. There is another way to write it. You can also write it in the following way. You can complete a diagram, or maybe I will write it here. It may be better. I will save a bit space. So if you take B prime, a sub-representation here, you can take F minus 1, I mean the converse image of B prime, which is of course going here. And okay, you have that. And then you can take G of B prime, which of course has some module here, and it gives a commutative diagram. It's not difficult to prove that it's also a short exact sequence that appears below. So, as a consequence of this thing, first of all, at least from a combinatorial point of view, you know that you arrive here. I mean, the dimension of that plus the dimension of that will be the dimension of this. I mean, when you have a short exact sequence, it always gives that. And this is kind of an algebraic map, so I will not say too much about it. Here I wrote a disjoint union. You can give it an algebraic meaning, but it's not really my point here. So say that instead of telling you what is the algebraic variety structure of this thing, I will just tell you the following thing. If I restrict phi e to the preimage, so to phi e minus 1 of some gr e prime of A cross dr e double prime of C. Of course, if you do that, it gives you a map from this restriction to one of the components. This is algebraic. Not difficult. It just needs a bit of work. So this is algebraic. And this is this map which will permit us to understand how, for instance, if you have this short exact sequence, how you can compare Grassmannians here and Grassmannians here and here. This is essentially this map which will do the job. Do you have any questions about this map? Is this reasonably defined? Okay. So, yeah, this is exactly the point. I create an ambient space. So you have several ways to understand it. The really naive way that you can understand it is that it's just a naive union. So it means that whenever you take somebody here, you will put it somewhere in one of these copies, which is exactly what it does, because this thing will have a dimension vector, this thing will have another dimension vector, and the sum will be E, because it fits in the middle of these two. So if this thing has dimension vector E, the sum of these two dimension vector is E. Okay, so if you take somebody here, it gets into one of these things. Okay? Actually, you could define what is a union of algebraic variety. I mean, there is a kind of categorical construction which permits you to do that, but I don't really need it. I mean, it's yeah. I don't need that. I just need to know that each time I have a point, it comes in one of these copies. And I also need to know that when I restrict to the good place, then it's an algebraic map. So I don't want to define what is a categorical coproduct or that, and it does not really matter for me at this point. Okay? So now I have this thing, and I want a first theorem or proposition, which will be the starting point of the story. Proposition. So if I take A prime, C prime in GR, okay, this is, my GR is super GR, E prime of A cross GR, E prime prime of C, so I fix E prime and E prime prime in this thing. Then I want to understand the fiber of that, because I remind you that I had some tool for Euler characteristic which permit me to compute Euler characteristic of something, or to relate the Euler characteristic here and there when I know the fiber. So what is the fiber of that? So phi minus 1 E, so E is fixed and E prime plus E prime prime is E, of A prime C prime is equal to either the empty set, this is possible, or an affine space. So I will write it like that, a translated of k to the n. This means an affine space. Okay, so we have that. So how to prove that? I will prove it very fast, and you will see it's kind of very elementary, actually. So I want to understand what is the converse image of that. How do I do that? So I start by understanding this diagram naively for each vertex. So what is this diagram for each vertex? I can write it like that. So I have my AI. So I fix I in Q0. I have my AI. Then here, I have a middle term, and then I have Ci. But if I consider just vector spaces, you know that all short exact sequence split. I mean, this is something that you know, I expect you know. Therefore, actually, you cannot have very much. Here, you can decompose it like that. It's not canonical, but I decide to decompose it in such a way. And when I write like that, you should understand this as a natural inclusion and this as a natural projection. So at the level of a vertex, my short exact sequence look like that. Then what will happen? Here, I have an AI prime which is included here. And here, so maybe I will put that, give it a name. Maybe I will call it, I don't know, iota prime, why not? Then it goes to some, in the same way as before, AI prime plus Ci prime, and then here's Ci prime. So here it seems that I don't have so much choice. It's actually the case. I will write, call it iota prime prime. But I still have a bit choice. Here, what can I put? So this is an easy computation about commutative diagram. So I let you do it, and I will copy it from my paper in order to not do mistake. So my matrix, the diagonal thing will necessarily be iota prime and iota prime prime if it commute. Then I have also something else first, and I really want to not spend time, so I do like that. Maybe, yeah, okay. Maybe sometime I will put an index I. Maybe I put an index I. I'm sorry, it become a bit more difficult. So it's an index I. And here I have some freedom. So I will call it Mi. Okay? So it means that at the level of vector spaces, so if I forget that this thing is a diagram of representation, if I just look at subspaces that I can fit here, this is very easy to describe the freedom I have. It's parameterized by matrices. Okay, the Mi are matrices. So Mi, how should I say? Yeah. If you do the same exercise or you study the same map, but you forget about the module structure, just you look at sub-vector spaces, you obtain something which is clearly an affine space. So Mi, where is Mi? Mi is a matrix with, so how many rows? I need to know the rows, so probably E prime I. And how many columns? E prime prime I. This is just a matrix with coefficient in. Okay, so I have that. And then what do I need? I need to add my condition that is actually a subrepresentation. So how to do that? First of all, if I take Q, so if I take Q in Q1, now I fix a Q going from to J in Q1. Then here, I have a map. I will write it in yellow. Okay, now it starts to be more difficult to read, maybe. But I will have something going to AJ plus CJ. Okay? And what can be the form of that? Actually, it's not very difficult to check. Everything which is omitted is exercise. So please, if I omit some check, you can check it. So what can be this arrow? This arrow is forced to be of the following shape. It should be big AQ here. So what is AQ? I remind you, A prime Q. So I remind you, big AQ, sorry. So big AQ, big CQ, and something that I will call beta Q here, and 0. So if you look at the condition for this to be actually a short exact sequence of representation, then you will discover that the condition forces the arrow from this thing, which is actually, you should understand it as something being B index Q. B index Q, the map. If you put it in this basis, it has to have this shape because of this short exact sequence. Okay, this short exact sequence forces it to be in this like that. Okay, so now you almost know what you need. We need the following thing. I hope that my explanation was clear, because from now on it will be almost straightforward. I need the following condition. I need that, I will write it like that. I need that image of AQ, CQ, BQ, 0 time iota, iota prime I, mi, 0, iota prime I is included in the image of iota prime j, mj, iota prime j. This is what I need. What is written here? So, of course, for all q, I need this. So what does it mean? It means that actually I choose my sub-vector space here. At this point, it's only a sub-vector space in such a way that the arrow BQ restricts to it. This is exactly what is the definition of a sub-representation. I want that this thing restrict to that thing. So, and this is the condition to make that it restricted. Think about it. And then now, I just help you slightly to do the computation, but it will be essentially an exercise. It's equivalent to the rank of the following matrix is determined. So I will write a matrix. So here I put iota prime j, mj, 0, iota prime j. Then after I write, sorry, it's not in this direction. I write the following thing. It's AQ, AQ iota prime I, 0, AQ mi plus beta q iota prime I, then CQ iota prime I equal EJ. So what I'm telling you is that saying that the image here is included in the image here. So first of all, maybe I should say that the matrix I wrote here is just this product. So the image of this thing is included on the image of that thing only if, when you put these two matrices together, the rank does not increase with respect to this one. Of course, the rank of that is the dimension of the image of this one. And if you put them together, what do you obtain as the image of that? You obtain the sum of the two images. And the sum of the two images should be equal to this image. Therefore, you should not increase the dimension. This is all what I mean by that. And then, you can do several computations, which essentially are colon operations as you did in your favorite linear algebra class, column and row operation, which don't change the rank, and you obtain iota prime j 0, 0, iota prime prime j 0, 0, aq mi bq plus bq iota prime prime I minus mj c prime q, and here 0 equal ej. So here I just use certain identities I know to kind of, for example, I can cancel out that. So maybe I can give you a hint. I can cancel out that because I know that aq iota prime I is equal to iota prime j a prime q. Why do I know that? Because this thing states that this is a submodule. So as I know that this thing is a submodule, I know this identity. Think about it. It's exactly what it means to be a subrepresentation. But then, using this identity, I can cancel out this column by some subtraction here. And so on. You can do all the things you need to do that. But this, I claim that this is a linear system of equations. So now, you will go really back to your first year linear algebra. This is a linear system of equations in terms of mi and nj. Why that? Because iota prime j is basically an inclusion. So you could imagine that this is just the identity matrix and some 0. In which case, this rank will be this one. In the case where the lower part, so you can imagine this as identity matrix and 0, and you want that the image of this thing is also included in that, and the way to do that is just to cancel out certain coefficients. Therefore, it's a linear system of equations. What are the solutions of linear system of equations? These are exactly translated of Kn or empty set. Because here, with second member, do we say that? I think we say that in English to say the second member. So it's not something like a of x equals 0, it's a of x equals y. Therefore, there might be no solution, or there might be solutions which are translated of Kn. So why there is a second member? Because this thing does not depend on mi and mj, it's a constant, okay? So you have a second member. Okay, it somehow should convince you of what I said. Sorry it was a bit long, but I think it's interesting that you can, to see that you can reduce this kind of argument to very down to the earth computation, right? So I start to identify Grassmannian of subspaces to something which is a vector space. So these are Grassmannian of subspaces, essentially communicating with that. So at each vertex, I have that. And then I add up the conditions, which turn out to be a linear condition in terms of this mi, okay? So, of course, I have plenty of such conditions. I add up the one for all the cubes, but it gives you a big system of linear equation in terms of the mi, in terms of the combinations of the coefficient of the mi and the mj, and then just solve it, or don't solve it, just remember that you know that it's empty or translated of Kn. This is just what I want. Okay, now that I have that, everything will become much easier. So this is somehow the key point of the story. So now that I know that, maybe I need to erase the proof because I need some space. I will keep the proposition because the proposition is important. And then I will give you a first corollary. Corollary, so how did I write it? The Grassmannian of E submodule of B is equal, in terms of Euler characteristic, to Euler characteristic of the image of phi E. I will not write the proof, I will say it orally because it's really straightforward at this point. How do you do that? You essentially say that, okay, when you look at phi e, you can decompose that in the term of the image of phi e and the complementary. Of course, over the complementary of the image, the fiber is 0, so it has Euler characteristic constant equals 0. On top of the image, according to this proposition, the fiber is an affine space, so it has Euler characteristic 1. And then you remember that you had a formula which tells you that when some map has constant Euler characteristic, the Euler characteristic of the domain is the Euler characteristic of the codomain times the constant value. So you just, separate this thing in two parts, the image and the complement of the image. Okay? And using that, you find that. So now you already have a kind of understanding how to relate the Euler characteristic at the middle to the Euler characteristic on both sides. It starts to become closer to what you want. Okay? I hope that it's clear. And then it will permit me to prove the theorem. Before I will ask you a corollary / exercise. So my corollary / exercise is that if you write xa times xc, you have xb plus some correction, and the correction is the following one. It's the sum for e prime plus e double prime equal e of what? Of the, okay, this is right. Is it really what I want? No, it's not what I want, sorry. It is what I want, sorry. Yeah, it's what I want. Of the Euler characteristic of the Grassmannian of E prime of A cross Grassmannian of E prime prime of C minus the image of phi E. So this is a complicated Euler characteristic times the product for I in Q0 of, so xi to the minus E prime plus E prime prime delta I minus, okay, so, sorry, I did some mistake. I will correct it immediately. Delta I, okay, sorry, now I really need to erase that as well. Dimension of B minus E prime plus minus E prime prime. So sorry about this. This is not quantified like that. It's just you need to take all possibilities in n the Q0. Of course, E is not fixed anymore. I mean, I have no a priori. So how to prove that? This is the easy part I was speaking about. Essentially, you take the product of these two things, and you just expand everything. And the only point is that when you will expand everything by computing this product, some part of the Grassmannian you will obtain will be actually in the image of phi, and some will not. Okay? By the way, here I should say image of phi E prime plus E prime prime if I want to be consistent. So some part will be in the image of phi I, and some part will not. And instead of just keeping everything together, I separate the two terms. The part which is inside the image will give me, thanks to this thing, xb directly, and the part which is not in the image, but by definition it takes that, because what I wrote is the complement of the image, so there is no, yeah, it's kind of completely obvious, it gives you that. Okay. Do you have questions about that? it's a computation. If you are uncomfortable, please do it. It's really a straightforward computation. But now, I claim that the theorem will be relatively easy to prove. Indeed, look that all, at least 1 and 2, are clearly of this form, right? 1 and 2 are clearly of this form. So let's try to do 1 and 2. Let's try to do 1 and 2. So, proof of theorem. So 1. What short exact sequence I need to do 1? I need this short exact sequence. I go from 0 to m plus n to n. So this is a split short exact sequence. Now, I claim that in this case, image, okay, I will write it like that, phi e is surjective. I will not write it, because what does it mean? It means that if you take a submodule of m and a submodule of n, or subrepresentation of m and a subrepresentation of n, you can lift it to or you can combine them into a representation of m plus n, which is of course obvious, right? So it means that phi e is surjective, but if phi e is surjective, this thing is 0, right? So I take a equal m, c equal n, and b equal m plus n. So the second term is 0, obviously, if this is surjective. So, okay, it's true. For that, I don't need anything, okay? Up to there, I don't need anything, or I don't need anything, at least no indecomposability. All this part work for any ABC, and actually, yeah, phi e surjective is just some kind of trivial remark that if you have a direct sum and you take 2 sub-representations, you can consider that direct sum as a sub-representation of the direct sum. So this is kind of completely obvious. And actually, you need it for something else than indecomposable, because actually I want this formula to permit me to expand a direct sum of a lot of indecomposable. So I want to be able to use it by induction, this formula. So yeah, certainly m and n are not indecomposable. I want to use it to decompose everything, right? Otherwise, I cannot tell you that 2 imply the exchange sequence here, because when I have xn here, I still need to write it as a product of the things which appear at the middle of the short exact sequence. Okay, what about 2? 2 is slightly more complicated. So I need to understand 2, and how I want to understand 2, I will say it like that. But it's very, okay. So I take now 0, I consider, as you can imagine, this case. Okay? I just take the AR sequence for ABC. And I want to understand what is the image of phi e, because here I need the complement of the image of phi e to understand. I claim that the image of phi e is everything, okay, I will write it like that, I'm sorry, except one thing, which is the pair 0m. So as long as your submodule are not 0 here and m here, you can lift. And this is because it's an almost split sequence. A near sequence has the property that it's close to be split. It's as close as possible to be split. So the reasoning I gave here is not true, but almost true. So you have very few things that you cannot lift to the middle term. This is the idea. The almost split sequence is almost split, right? So it's very close to that. And then you have only one thing missing. I will try to explain you why you have only one thing missing. I hope that it does not become too technical. But the idea is the following thing. suppose I take some point which is not this one. So I take, I take some submodule, I don't know, I will call it A prime, a submodule of tau m. And I take C prime, a submodule of M. And I try to lift this to N. So what is the idea? The idea I told you already that the following bilinear form is non-degenerate. So if I take morphism from A prime, I want to do like that, to tau m. So this is one morphism. I will call it iota prime, and this one iota prime prime. I'm sorry, the notation are a bit confusing maybe. So if I take a morphism here, and I compose with an extension, so sorry, I copy because I don't want to lose you too much. So M A prime. So you remember that when you compose that, you arrive to x1 tau m m. And I remind you that I fixed something which is almost arbitrary to k, but which map an AR sequence to 1. And this is the way, I told you this thing is non-degenerate, it's not that difficult to prove. This is the way I used to prove the so-called AR duality, which is maybe not the best method from a certain point of view, but I think it's very visual from my point of view. So you have that. And now, what can you do with that? But first of all, if iota prime is non-zero, so I will do two cases. This I want to keep, I'm sorry. Okay, I want to keep that as well. Now I start to feel that I want to keep too many things. Okay, I will try to finish the argument here then. So if iota prime is non-zero, okay, I will write a short version. There exists a psi in this extension in x1 m a prime such that iota prime composed with psi is equal to the AR sequence. Okay? Because if you take something non-zero here, by definition of a non-degenerate bilinear form, you can complete to something which is mapped to 1, and you can prove that. But what happens if you know that? Essentially, it permits you to prove that you can complete the diagram. So exercise, it implies that you can complete the diagram. Okay? Now, there remains the case iota prime equals 0. But if iota prime equals 0 and iota prime prime is not a split AP, then you use the equivalent characterization I gave you about AR sequence. It permits you to factor iota prime prime through the middle term of your exact sequence, and it's exactly what you need to lift it. So if it's not a split epimorphism, then okay, by definition, or by second characterization of AR sequence, by definition of AR sequence. So there is only one case that I did not deal with, is iota prime equals 0, and iota prime prime split epimorphism. But a split epimorphism, which is also an inclusion, is just an equality or an isomorphism. So last case, this is you take you take m and 0. Okay, so last case, you take 0m. So the only case I didn't deal with is 0m. However, 0m cannot be lifted because to be able to lift 0m is equivalent to split this short exact sequence. That means to rewrite this as a direct sum of these two terms. But by definition of an AR sequence, this is not the direct sum of these two terms. Okay? Therefore, I have this thing, and once you have this thing, it's somehow straightforward. You apply that again. Now you know that this complement is just essentially 1 point. I say 1 point is actually an affine line, but it's all multiple of R sequences essentially. So it will work. I don't want to. It's a split sequence. No, actually it's a point because okay, it's really a point. So you have only 1 point here, and just compute it. In order to compute, you need to use the following thing. Maybe I write it here. You need to use the following thing. You need to use that dimension of M, dimension of N, plus dimension of, so this is a general identity, N dimension of tau M equals 0. But this is just the AR duality, or it's a rephrasing of the AR duality to know that this sum of two sigma is equal to 0. So just compute by using the formula with Rho and X, and you will recognize the AR duality in this thing. And this is the only thing you miss to actually compute this funny term. Now you have you have 1 point, and you just need to compute the exponent and to see that the exponent is actually 0, right? Okay, so 2 is done. For 3, maybe 3 is also interesting because it's a bit of different nature, so I will do 3 as well. I promise you that it's the last bit of technical thing I do today. Let's understand how works 3, because it's also an interesting application of structure of projective modules. If you did not really grasp the description of projective modules over quiver yet, you can understand it via this proof. So 3. My claim is the following one, is that the projective at vertex I can be written like that. It's a symbolic notation, and I will explain you what it means. There is just a vertex that I call K, because it's a K as K vector space, but at vertex I. And then I will write it like that. I will explain in 1 second what it means. Over a quiver, projective looks like that. For all arrows I, sorry, it's GL, means there are plenty of, or only a few, whatever, you don't care, there are a certain number, for an indexation of I to JI. So why that? You remember, I think it's Pierre Guy who did that, who told you that a basis, is it you? A basis of projective module was given by the passes in the quiver starting at I. So what can be a path starting at I? Is either the Lévy path at I, or a composition of one arrow and a path starting from the end of this arrow. And this is exactly what I wrote. Because what is a path starting at J1? It gives a basis of Pj1. So I can understand Pi as this Lévy path and all projective at J1. So I have a basis which consists of one element here, and the union of the disjoint union of all the bases here, and I symbolize it like that. And what does it imply? It implies that a submodule, that subrepresentation of Pi are of two kinds. Pi itself, of course, it's a subrepresentation of Pi, or subrepresentation of Pj1 plus Pj2 plus ... Pjn. So the only thing that I didn't state very clearly at this point okay, maybe there are other things, but the only thing I didn't say is that when you look at a subrepresentation of something like that, it needs to go bottom up. So each time you have something, you have everything below. Therefore, if you have this point, you have all. And if you don't have this point, it means that you are a sub-representation of this thing. So you have only these two cases. But what does it mean? It means that you can rewrite. So let's try now to compute xpi. We'll just compute xpi with the formula. What is xpi? There is one term which is coming from this sub-representation. So let's look at this term coming from this representation. Now I'm looking at this formula. So I have one term coming from this representation. Of course, the whole submodule, there is only one point, so it's just characteristic 1. And if you compute, you will obtain, I will copy it because it's not very interesting thing. It's the product, the first term is the product from j is q0 of xj to the minus dim I delta j. So this is the term which corresponds to the whole submodule, the whole pj as a submodule. And then, and I let it somehow as an exercise, the second part is x pj1 plus pjl times pi for j to I in q1 of xj times xi to the minus 1. Right. Yeah. So you have that. So pay attention that here I was a bit fast, but essentially the idea for computing the second term is that most of the part of the second term comes from the direct sum. And just your exponent change a bit because here I have a dimension of m. And so there is a discrepancy between the dimension vector of this pi and the sum of dimension vector of this. And this discrepancy will kind of add a factor here. So this is just because, yeah, you cannot just identify the sum of the other term to that because you have dimension change in between, so the formula changed slightly. Okay, but just think about it, it's not that difficult. And this you can prove. It's not very difficult either to prove that right. I can explain you why it is. It is that it's just xi to the minus 1. And why it is that? Because you can prove the following thing. You can prove that dimension, the Euler form of dimension of pi, this is an underlined dimension, and delta j is just the Kronecker symbol of delta ij. And why that? Let me explain why that in 1 second. So you are looking at this formula. So you are looking at the number of morphisms from the projective at I to the simple at j. And of course, the projective at I is mapped to the simple at j non-trivially if and only if I equals j, because the projective at I is the projective cover of fj. And okay, think about it. This is one only if and only if I equals j. So if you have pi and sj. And as pi is projective, there will never be extension here, so this term is always 0. Okay? So you have this thing. All what I don't say explicitly is an exercise. Okay? And if you look at that, you can rewrite it as the 3 here, just by multiplying both sides by xi. Okay? So it's not that difficult to prove that, and I would like to convince you that actually, in a sense, everything was encoded already in this, in the lemma which says that, or this lemma, if you want. This lemma kind of is the lemma which makes everything work. The other thing is somehow some kind of a bit relatively easy computation or easy analysis of this thing. What a priori is not obvious, it's not difficult to prove, but it's not obvious intuitively, is that the other part is just like, yeah, you actually compute the image and you try to describe the image of phi. Okay, so for the last 20 minutes, my aim, so I proved the theorem I wanted to prove. However, you were teased by Pierre and Bernard about much more general situation, and I would like to explain you how this kind of thing fit in the most general situation. So I will not anymore do rigorous proof. I don't know if you find that this is rigorous proof, but you can make it rigorous easily. Now I will more try to give some intuition of how to extend it to the whole case. So you remember from talks of Bernard and Pierre that, first of all, you can extend this module category to a cluster category, which look now the module category plus the orange part, as in the talk of Pierre. And the orange part is, of course, identified on both sides. You recognize the same. So these two parts are identified. This is folded. And then the claim is that you can map things here via the cluster character that you need to modify a bit to take in account this thing. So, but the cluster character is decomposed in two parts. One part is what Pierre denoted F. So what was F? It was a functor, and here I will cheat a bit with respect to what Pierre said. It's just home. I will call it T0 blank. So it's a functor which takes the morphism from T0, where T0 is my initial cluster tilting object. So here, T0 is the sum of projective. Okay, T0 equal P1 plus P2 plus P3. Then by doing that, you go to mod, okay, no, rep Q. Okay, I will write it rep Q. Okay, maybe some remark. Here I didn't write CQ, I wrote CQ up if I want to follow the convention of before. So it's CQ up, but never mind, does not matter. So you take rep Q, and if you take X, what I wrote X, it's almost that, except on the orange part where you need to modify a bit. But for the non-orange part, it's actually this composition. So pay attention. It's true because I'm speaking about a quiver. I might give a comment later about that if I have time, but it's true because I have a quiver. The formula that Pierre gave is essentially this functor composed with this thing. Okay, so we have that. And now, what you need to do if you want the general thing. So if you want the general thing, you cannot only do these three cases. Because these three cases, the fact that by doing this lazy mutation, you will obtain all cluster variables is actually linked to the fact that you are in linking type. If you are not in linking type, you cannot prove that by mutating only at single source, you will have all clusters. So you need something more, right? Unfortunately, these mutations, I mean, this corresponds to a mutation. These mutations are not enough to cover all cases. So how to solve that? I will try to give you some intuition on how to solve that. Okay, now, okay, I will erase that. Please try to remember roughly what it was looking like. Now I need more. I need what Pierre was saying yesterday. I need the following thing, that you have a mutation of cluster tilting object. So what does look like the mutation of cluster tilting object? It looks like that. So you take, so first of all, you want to lift big part of the reasoning to this part. So what looks the mutation of cluster tilting? You have T cluster tilting. So cluster tilting is almost like maximal rigid. The summands are rigid, and if you don't remember the definition, it's just a kind of maximal rigid. So you take T cluster tilting, Ti a summand. So here I will borrow a notation of my Japanese colleague. I'm sorry, I don't know if it's a standard notation. So this is a notation which is used in Japan for saying Ti is a direct summand of T. that I take indecomposable. Okay? So I take an indecomposable summand of T, and then Pierre told you that if you do what we called add T minus Ti approximation of Ti, okay, it's a basic, by the way, but as in the context. You will do that, so E is in add T minus, yeah, T, okay, T over Ti, I should write it like that. And then you will have a code, which is Ti star, as in the talk of Pierre, and then you go to sigma Ti, okay? And then what Pierre told you is that if you do Ti star the same with Ti star, you will come back and this is essentially because the category is to Calabi-Yau. I mean, okay, plus the fact that you have a cluster tilting object, plus the fact you have no loops and no two cycles, probably. So yeah, sorry about this simplification, but yeah, I'm explaining in this case for now. So you have that, and then you do the following thing. You apply the functor f. So I will apply the functor f without. You apply f everywhere, and it gives you an exact sequence. It's a part of the long exact sequence which was described yesterday. So there are two exact sequences. Pay attention, they are not short. I'm not saying that this is injective or whatever of this kind. They are just exact sequences. And then you do the same as before. You do the same as before, so let's call that 1 and 2. Define a phi E, a phi E1, maybe, which goes from this thing, so it goes from the Grassmannian of E-dimensional submodule of Fe to the union for E prime and E prime prime. It's always dimension vector of Grassmannian of submodule of Fti and Grassmannian of E prime prime module of Fti star. You have this thing. Pay attention, I didn't put that the sum is equal to E because in this case you can have some overflow on the left or the right. I mean, you know when you have short exact sequence, you can control the fact that the dimension vector of the middle term is the sum of the two dimension vector, but you don't have that anymore. So you just know that you're right. Yeah. Okay, so you have this phi E1, which basically take an element here, take its pre-image and this image, yeah, an element, a sub-object, and you can do it for the other one. So you can start by phi E2, 2, sorry. So what do I do? Phi E2 will start from the Grassmannian of E submodule or subrepresentation of Fe prime. But now I can also map it here. Of course, it's a slight change of notation. I just change the order of this product, but it goes to the same space. And the trick is the following one. It's not that difficult to prove, or it's a bit difficult. You can explain slightly. No, I will not explain the argument for true, but I can tell you where it comes from. You have the following thing. You have that. So, image of phi E1 union image of phi E2 is equal to all. All meaning all thing. So what does it mean? It means that now, when you do your expansion, instead of having almost everybody or everybody on one side and almost nobody on one side, it becomes more balanced. One part of the term of your product will go into here and the other part here. So what do you will obtain? You will obtain that x, okay, I will write it with Cc. You will obtain that Cc of Ti, Cc of Ti star. So what it is, by using exactly the same idea as before, it's just Cc of E plus Cc of E prime. Okay? You have two possibilities. Maybe a remark to make it maybe a bit more clear even. Remark, if you take, now you go back to this situation, I just want to tell you that the following thing, that M0, tau M is sigma M in the cluster category 0, not 0, sorry, okay, equal sigma M, is the only triangle of this only extension in terms of triangulated category from tau M to M. Okay, so it's kind of a remark. It explains you, it reinterprets the fact that here you have a 1 appearing. This 1 comes from this only extension in the converse direction. So pay attention, this is something that you don't see in the module category. It's an extension which goes through the orange part. Okay? Otherwise, you have no map which permits to go back from one module to its tau. So you need to kind of do anything like that. Okay? So it's because you folded. This triangle does not come from a short exact sequence in the category. It's something new. Okay? Okay, so it permits you to obtain this formula. So of course I did not do it in very much detail, but it's not that difficult. So maybe the only thing is if, again, this is mainly up to some other thing, to Calabian-Onnes. So to Calabian-Onnes tell you the following thing. It tells you that, right, first of all, it tells you that if you have an extension in one direction, there is one in the other direction, because to Calabian-Onnes identify ohm m sigma n to ohm n sigma m, so x mn to x nm, so to the dual, sorry, to the dual. And the point is that it does it functorially, and by using the functoriality, you can understand that. Okay, so this is a bit more general, or actually it's much more general. And why it's much more general? Because actually, this thing, you don't need to apply it in this T0. You could apply it in any cluster tilting object. Any cluster tilting object is okay. Modulo the fact that you need to modify a bit the Euler characteristic, because sometimes cluster tilting objects have endomorphism algebra which are not path algebra. So the formula as I wrote it work for when the cluster tilting object has an endomorphism algebra which is a path algebra, which comes from a quiver. If it's not the case, then you have something where the x2 exists. So you remember my long exact sequence, which was not so long, stopping at x1. You need to go further, and therefore you need to modify essentially, I would say that, in a way which is kind of related to the formula that Pierre wrote on the blackboard. So you need to replace the formula I used by the formula of the blackboard. However, even for that formula which is modified, the difficult part is still embedded in chi, gre, blah, blah. It's not embedded in that. This is still the combinatorial easy part. The form and the linearity there, not the difficult part. The difficult part is really in the Grassmannian, and this is somehow the sketch of the proof for the Grassmannian. Okay? So you have that. And then what should I say else? This is something which have not been said before, and I will not, of course, define them, but a remark you can create, and I will put quotation mark because otherwise people will think I'm writing weird thing. CQ, where Q is not a cyclic. So I say in a few words, so if Q is not a cyclic, you can put a generic potential, so it has been discussed several times. And there is a notion of cluster category for for quiver with non-degenerate potential. So it was studied by Claire Amiot. And the definition is complicated. But if you admit that you have a category which is 2 Calabi-Yau triangulated, when you can mutate, where you have one object with endomorphism ring, your quiver with potential, and you can mutate them without creating loop and 2 cycle. If you admit that, you don't check the construction, you just admit that this triangulated category exists, then you can do the same thing. You don't really need to understand the category deeply, you just need to know that it exists. Of course, the existence of the category is the difficult part of the story, but once you know that it exists, the same game works. And in a sense, it works even more abstractly. You don't even need to know that it's a cluster category. You need to know a certain number of properties on a triangulated category. This argument is pretty much, or even on some other kind of category called exact category. You can do all these things. Okay, so by the way, I did not give a credit to this thing. So I think it's Caldero-Keller mainly. And it's, okay, Amiot for the cluster category in general case, and it's Palu for the cluster character. If somebody disagree, please tell me in more general case. When I write like that, it does not mean that they work together. It means that they did two different things in the story. So cluster category exists. Palu shows that this reasoning, I mean, all the technicalities that I hide under the carpet and which actually exist, actually need to be worked out. And actually, Jan Palu did even more, so maybe I will finish by giving you something even more general. And I'm sorry, for those who are lost, it's not very important. It's just like in order to give a full picture of what can be done about this thing. So actually, Palu have proven in a quite big generality, which actually include at least all the cases I said here, the following formula. So he called that a multiplication formula, and I will try to explain you why it's interesting. Multiplication formula. So here, I'm interested in exchange formula. So one cluster variable and it's mutated and it's equal to the sum of monomial. But he tried to do it in general because he thought, why to stop here? Why not to try to compute xm, xn in general and try to rewrite it in terms of other things? And he found the following thing. I will explain. Maybe I will write like that. I need to explain a bit and this will be finished. So this is integral, but it's a finite sum, sorry. I will tell you in 1 second what it means. It's an integral along for all psi in x, in p x1 mn of and I will say middle term of psi. So read that as I parameterize the sum by the extension of m by n. I don't tell you yet how I parameterize them, but I parameterize my sum like that. So for each psi, I have a middle term, okay? Plus the integral for psi prime in p x1 nm x of middle term of psi prime. Okay? So this is true in several contexts. So I write it abstractly like that, and I will explain you in 1 second what is the integral. But sorry, I finish really very soon. The point is that in all the cases I described here, there is only one point in this space. Therefore, it's just one value, and it's just, I mean, you recover that. You have one here, and here you have exactly 1 point, so you do an integral over 1 point space, so it does whatever you want, what I mean like. And the point is the following one, is that you define the integral for a certain point in an algebraic variety x of f of v to be equal to the sum for all possible value of f of v. So f is going, say, from x to a vector space. So this is a vector space of, so all the possible value of v, so it seems a lot, of c times the Euler characteristic of f minus 1 of v. What is that? It's essentially computing an integral with respect with respect to the measure given by the Euler characteristic. You can do that because actually you restrict to the f which have finitely many different values. Okay, so actually f is so-called constructible. I will not define what it means, but this is what permits you to actually write this expression, which is simplified into this. And yeah, you try to give a sense to that. So what does it mean? It means that whenever there is extension between m and n, you can somehow, I would not dare to say to simplify the product xm times xn. So xm times xn is also xm plus n. But the intuition is that kind of m plus n has self-extension, and you hope to write it in function of things which have less extension. Of course, it's not completely true, but this is the idea. Of course, this formula is empty if this thing is empty. So if m plus n is rigid, this is 0, this is 0, this is 0. So you don't gain anything. So if you are in the same cluster, you basically cannot do anything. However, if you have not self-extension, if you have extension between m and n, it permits you to write it in terms of other things which morally should have less extension, and which have actually less extension less self-extension when the dimension of extension is 1. Okay, I will stop here. So the last part was not supposed to be understood deeply, just to give you a kind of, I don't know, a kind of larger view. I don't know if I succeeded about what other thing you can do about this thing, how you can enlarge your view of this thing. And I hope that it works. Thank you very much.